Good afternoon, Nashville. I'm Dave Aronson, the T-Rex of Codosaurus LLC, and I'm here to teach you to kill mutants. But first, I think we need to level set some expectations. To call this an advanced talk might be a little bit misleading. To call it an introductory talk, though, would be even more misleading. What this is an introduction to an advanced talk. To an advanced topic. So if you're already well-versed in mutation testing, I won't be too offended if you go seek better learning opportunities, but I'd still rather you stick around so you can correct my mistakes later in private. And I mention mistakes because I'm not an expert on mutation testing. One of the dirty little secrets of public speaking is you don't have to be an expert. You just have to know a little more than your audience and be able to convey it to them. And mutation testing is still so rare that most developers have never even heard of it. So let's start with the basics. What on infinite earths is mutation testing? In our universe, that of software development, not comic books, of course it's a software testing technique. Surprise! You might look at the name and think, well, it's obviously about testing the mutations used in genetic algorithms. But no. It's about testing our code and also our unit test suite by using mutations. Its primary benefit is to help ensure that our tests are strict by finding the gaps in our test suite that let our code get away with unintended behavior. And once we find these gaps, we can either add tests or expand and improve our tests to close up those gaps. And this lack of strictness comes mainly from lack of tests or poorly written tests or poorly maintained tests that didn't keep pace with changes in the code. Speaking of which, it can also help improve our code by helping to ensure that our code is meaningful, by which I mean that any little change to the code should result in a noticeable change in its behavior. Lack of meaning generally comes from code being unreachable or redundant or otherwise without any real effect. And once we find code like that, we can either make it meaningful if that fits our original intention, or just get rid of it. Mutation testing puts these two together by ensuring first that our code is meaningful so that the change it made had a noticeable effect, and then that our tests are strict enough to notice that change and fail. Now, not all the tests have to fail, but each change should make at least one test fail. Mutation testing does all this by mutating copies of our code, hence the name, and it does this with the intention of creating test failures, otherwise known as faults. So mutation testing can be categorized as a fault-based testing technique. And this means it is sort of related to something you might already be familiar with, Chaos Monkey from Netflix. Just like Chaos Monkey helps Netflix find flaws in their error recovery process, mutation testing helps us find flaws in our test suite and in our code. But the way mutation testing works is sort of upside down from how Chaos Monkey works. Chaos Monkey does a lot of things, but it's best known for injecting faults, such as dropped connections, into Netflix's production network. And if all goes well, in the sense that Netflix's customers don't notice, then they know that their error recovery is working well. Mutation testing, however, injects semantic changes. It doesn't know whether these changes are going to result in faults or not. Well, we certainly hope they all will, but that's up to the test suite. It puts these changes into copies of our code, not our actual network. And it does this all in our test environment, not production. Whew. And lastly, if all goes well, in the sense that our unit tests all still pass, that does not mean everything's great. That means there is a problem. Remember, each change should make at least one unit test fail. But there are some drawbacks, so it is not quite a silver bullet. As we developers know, there's no such thing. Besides which, those are for killing werewolves, not mutants. The first drawback is that it's rather hard labor on the CPU, and therefore usually fairly slow. We won't want to mutation test our entire code base on every save. Maybe over a lunch break for a smallish system, or overnight or over a weekend for a larger one. Fortunately, most tools include an incremental mode, so we can just check what has changed since last time we ran our mutation testing. That we might be able to do on every save for a very small system, or at least over a much shorter break for other ones. Its CPU-intensive nature can also really run up our bills on cloud-based systems such as AWS or Azure, or however you pronounce it. Another drawback is that it is not at all a beginner-friendly technique. Mainly, it tells us that making this particular change to the code made no difference whatsoever to our test results. But what does that mean? It takes a lot of interpretation to figure out what a mutant is trying to tell us. Their accent is very strange, and they are almost as incoherent as zombies, but with a much larger vocabulary, so they're not always on about brains. They're usually trying to tell us that our code is meaningless, or our tests are lax, or both, but it can be very difficult to figure out exactly how. And worse yet, often it's a false alarm. The mutation might not have made any tests fail, but it didn't really make any actual difference either. It can still take quite a lot of time to figure that out. And even if a mutation did make a difference, there's still quite a lot of code that we shouldn't bother to test. Like if you have a debugging statement that says the value of x is, and then the value of x, that constant part, the string, the value of x is going to get mutated, even though we don't really care about that. Fortunately, most tools do have a way to say, don't bother mutating this line, or even this whole function or method, whatever. But that's usually done with comments, which can then clutter up the code and make it less readable. Now that we've seen some of the major pros and cons, what exactly does mutation testing do and how? So let's peel back one layer of the onion and look at a high-level view. First, our chosen mutation testing tool will break our code apart into pieces to test. Usually in Ruby or other object-oriented languages, this will be our methods. And then for each one, it will try to find the tests for that method. If the tool can't find any, then some of them will use the entire test suite, which is horribly inefficient and leads to a lot more false alarms. But most will just skip that one method and go on. Better yet, a lot of them will warn us, so we know we should go add some tests. Assuming that we're not going to skip this particular method, next the tool makes the mutants. And to do that, it looks closely at exactly how it can be changed. And for each tiny little way that method can be changed, the tool will make one mutant with that change in it. And once it's done creating all the mutants it can from one particular method, then it will iterate over the list. And now we get to the heart of the matter. For each mutant derived from a given method, our tool will run each of that method's unit tests, but using each mutant in turn instead of the original function. If we get down to one test that fails, that is called killing the mutant, and that's exactly what we want. It's a good thing. It means that first, the code was meaningful enough that the tiny little change it made to create that mutant did have a noticeable effect on the behavior. And secondly, that at least one of the tests was strict enough to spot that difference and fail. After that mutant has made that test fail, generally the tool will stop running any more tests against that mutant. We don't care how many more it could make fail. Like so much in computer science, we only care about ones and zeros. It will then move on to the next mutant, or if that was the last one from that function or method, move on to the next method. But if a mutant survives all those tests, meaning it lets them all pass, then it has the superpower of mimicry, skilled enough to fool our tests. And this usually means that our code is meaningless, or our tests are lax, or both, and now it's up to us to figure out how. Now let's peel back another layer and look at some of the technical details of exactly how it does this. First, our tool parses our code into an abstract syntax tree. I know some of those boxes may be rather small to read from back there, but we don't need to understand this AST in detail. And also some tools do it slightly differently. They work against bytecode rather than an AST. Some proof of concepts and such may even work on actual raw text, but most of them use an AST. So let's just roll with that. After our tool creates an AST, then it traverses it, looking for subtrees, or branches, if you will, to represent our methods. And after finding them, then it treats them basically like I said before, looking for their tests and running them. But how does it look for the tests? That usually relies, at least partly, on us developers either annotating our tests or following some kind of naming convention. But this is sometimes augmented, maybe even completely replaced by the tool looking at what tests call what methods, though this can get a little tricky if the method is not called directly from the test. After the tool has found all the method's tests, then, assuming it's not going to skip this method because of lack of tests or whatever, it makes the mutants. So how do we make mutants from an AST? It traverses that subtree just like it did to the whole thing. But now, instead of looking for even smaller subtrees like twigs or something to extract, it's looking for nodes where it can change something, where it can replace that with another kind of node. For each one of those that it finds, and for each way that it can change that node, then it'll make a fresh copy of that method's AST subtree. For instance, suppose our tool has started traversing that AST I showed earlier and has gotten down to this not equal comparison by following those red arrows there. And for each way it could change that node, it would make a fresh copy of this entire subtree with only that node changed in that particular way. And once it's done doing that for that node, it would continue traversing the whole rest of the subtree and do likewise for the rest of the nodes. So I've said a lot about changes. It makes changes to this and so forth. But what kind of changes are we talking about? There are quite a lot. It could change a mathematical or logical or bitwise operator from one to another. In languages and situations where it can do so, it could even substitute one of a different category. For instance, in Ruby, we can treat pretty much anything as a Boolean. So x plus y could be changed to x and y, or x or y. It could change the order of operands in situations where that matters. Most of them are smart enough not to bother doing that with plus, but it'll do that with minus and divide and exponentiation. It could change a comparison from one to another. It could change, it could insert or remove, rather, a logical, mathematical, or bitwise negation. It could change a constant or variable or expression or function call to a completely different value, possibly even one of a different and even incompatible type, such as changing a number to a, if I may quote Smeagol, string or nothing. It could remove entire lines of code. It could remove a condition or a loop control. It could scramble or truncate arguments in a method call or a method declaration. It can replace a method's entire body with just a constant or either of the arguments, or raising a deliberate error, or nothing at all if the language permits, like Ruby does. There are many, many more kinds of changes it could make, but I think you get the idea by now. Now, from here on in the process, there aren't any other low-level details I want to add, so let's look at some examples. We'll start with an easy one. Suppose we have a method like this. Pretty simple. But think about what a mutant made from this might return, because that's what our unit tests are probably going to be looking at. And there are lots and lots, but mainly you could return all kinds of values like any of these. Expressions or constants and many more, but I had to stop somewhere. Now suppose we have only one test, like so. This is a pretty bad test. But even so, most of the mutants from that previous slide would get killed, the ones shown here in crossed out green. The ones returning constants are quite unlikely to match. 4 is not a very common constant to just randomly come up with or have any significance. Subtracting gets us 0, dividing gets us 1, returning either argument alone gets us 2, and even the ones that deliberately raise an error, or even accidentally raise an error, will at least make the test not pass. But addition, multiplication, and exponentiation in the reverse order also get us the right answer, and will therefore survive that particular test. And we know this because we run a mutation testing tool, and it gives us a report that looks something roughly like this. The exact words and format and amount of context and so forth will vary widely depending upon which tool we use, but the information should be roughly the same. And to unpack what that information is, it's telling us that if we changed the method called power, which is in file demo.rb starting at line 42, in any of 4 different ways, then all its unit tests would still pass. And then those 4 ways are to change line 42 to swap the order of the arguments, to change line 43 to change the exponentiation to addition or multiplication, or to change line 43 to swap the order of the operands. Pretty straightforward, right? Haha. So what is this set of surviving mutants trying to tell us? A good start to figuring that out is to ask ourselves, how are these mutants surviving? What is it about them that lets all our unit tests, or in this case our one and only unit test, still pass? The usual answer is that they give the same result or have the same side effects as our original method. And to determine how that happens, one useful technique is to look at least one mutant together with at least one of the unit tests it passes. So let's start with the plus mutant. Looking at that change, how it's changing the exponentiation to plus, makes it fairly clear that this mutant is surviving because 2 to the second power, what we expect to have happen, equals 2 plus 2. They're both 4. I assume you all know that much basic math. So how do we kill this mutant? The main way you kill a mutant is to make sure you have a test. You can either change the existing test or an existing test, or add a new test with arguments such that the 2 expressions come out differently. In other words, we just need to assert that some x to the y equals z, such that x plus y is not z. Easy enough. For instance, we could add or change the test to say this, that 2 to the third is 8. 2 plus 3 is 5, which is not 8, so that kills the plus mutant. 2 times 3 is 6, which is also not 8, so it also happens to kill the times mutant. And 3 squared is 9, again, not 8, so it kills the argument swapping mutants as well. Now, we didn't have to necessarily attack them all at once. We don't need to be a superhero about it. We could have said instead, as an intermediate step, that 2 to the fourth is 16. That would have killed the plus and times mutants without killing the argument swapping mutants quite yet. And then we could have added this or changed the test to this to kill those as well. Now, this may make mutation testing sound rather simple, but this was a nearly trivial example. So it was pretty easy to think up new arguments to make all the reasonable mutants return a different value from the original method. So there's lots of ways to skin that flurkin. So let's look at a more complex example. Suppose we have a method to send a message, like so. This method, sendMessage, loops over and over, sending in each chunk as much as sendBytes can handle in one shot, picking up where it left off each time until the whole thing has been sent. Now, a mutation testing tool can make lots and lots of different mutants out of this, but one of particular interest would be this. That's an example of removing a loop control. Now, suppose that this mutant does indeed survive our test suite, which consists mainly of this. Now, there's a little more to it that I'm not going to show quite yet, mainly setting the size and constructing the message. But even without seeing those parts, there is something that the survival of the non-looping mutant is trying to tell us. And that is that if a mutant that only goes through this loop body once acts the same, as far as our test suite can tell, as the original code, then our tests are not making our original code go through that loop body more than once. The question then is, okay, what does that mean? And you'll find that interpreting what mutants are trying to tell you involves a lot of asking yourself over and over, recursively, what does that mean? In this case, it means we're not testing sending a message bigger than what sendBytes can handle in one chunk. So most likely, we're just not testing sending a big enough message. For instance, we see here that our maximum chunk size, which is what sendBytes can handle in one shot, is 10,000 bytes. But we're testing with just a tiny little 3-byte message. So of course it's only going to go through that loop once. So how do we fix that? Should be pretty easy. Assuming there's nothing weird about the code preventing us from doing so, we just take the maximum chunk size as declared, presumably publicly, add 1, create that big message, and try to send it. But perhaps, to paraphrase Shakespeare, the fault, dear Nashville, is not in our tests, but in our code that these mutants are survivors. Perhaps we did try sending with the largest permissible message out of a predefined set of messages, or at least message sizes. For instance, here we have small and large messages, and we tried sending a large, and yet the non-looping mutant still survives. What could possibly be wrong with that? Is there anything wrong with that? What's it trying to tell us now? Now it's trying to tell us that a version of sendMessage with the looping removed will do the job just fine. This is an example of mutation testing finding redundant code. If we also strip out all the other stuff, that was needed only to support the looping, then it boils down to this. And now it's really clear that the ultimate message is that send message may well be entirely redundant. We could possibly just use send bytes directly. Now I say may well be redundant, not is redundant, because in real world code there may be some logging and error handling and whatnot that we need to put in send message. But at the very least, the looping was redundant. So what do we do about it? We can just chop out the looping, or if we don't need any extra stuff in send message, chop out send message entirely. And this will make our code more maintainable by getting rid of useless cruft. Fortunately, when it's this kind of situation, the fix is pretty clear. Just get rid of whatever it is that the mutant doesn't have. Now that we've seen a few examples of spotting bad tests and redundant code, I'd like to address a few frequently asked questions. First, this all sounds pretty crazy, deliberately making tests fail in order to prove that the code succeeds. Where did this whole bizarro idea come from in the first place? Mutation testing has a surprisingly long history, at least in the context of computers. It was first proposed in 1971 in Richard Lipton's term paper titled Fault Diagnosis of Computer Programs. The first tool didn't even appear until 9 years after that, in 1980, as part of Timothy Budd's PhD work at Yale. And even after that, it still wasn't practical for most of us, running consumer grade or desktop workstation grade machines as opposed to souped up servers or gaming rigs. Until more recently, maybe the past couple decades, with advances in CPU speed, multi-core CPUs, more memory, and things like that. But that leads us to the next question: why is it so CPU intensive? To answer that, we have to do some basic math. Suppose that our program has methods with typically about 10 lines each. And each line has about 5 places where it could be changed to about 20 different alternatives. That works out to about 1,000 mutants per function. And for each one, we'll probably have to run at least a few unit tests, anywhere from 1 if we get real lucky and kill it on the first shot, all the way up to all the unit tests applicable to that method if we get so unlucky as to kill it on the last shot, or worse yet, it survives them all and has to be reported as a surviving mutant. But suppose we wind up running just a mere tiny 10% of all the unit tests for the particular method on average for each mutant. Since we started with 1,000 mutants, that's still 100 times more test runs than just running our normal test suite. So if our unit tests normally took a zippy 10 seconds, mutation testing with these assumptions is likely to take about 1,000 seconds, which might not sound like much at first, but it's almost 17 minutes. But there is some good news. Over the past decade or so, there's been a lot of research on trimming down the mutant horde using techniques like weeding out those that are redundant with another mutant or semantically equivalent to the original code, or otherwise trivial, like they're going to raise an error condition that the tool can tell the code and the tests are not going to catch. Things like these have squished it down to about 1/3 under some very good circumstances. But even with that rare level of success, it's still no silver bullet, because this takes a fair chunk of CPU time itself, and the leftover mutants are still quite a lot. The last common question is, when making mutants, why change them in only one way? There are a few reasons. First, it helps us poor humans focus. It's much easier to tell what a mutant is trying to say to us if we're only talking about one thing in the first place. You can think of it like using the single responsibility principle. Another reason is that multiple changes may balance each other out for no net effect, leading to a lot more false alarms. For instance, remember that first trivial example and its argument swapping mutants? If one mutant had both of these mutations, then the first one would swap the arguments, and the second one would swap them right back for no net effect. So such a mutant would survive any unit test you cared to throw at it. Lastly, allowing multiple mutations per mutant would create a combinatorial explosion of mutants, with the tool making many, many times more mutants per method, which would make it even more CPU intensive. I'll spare you the math, but with our earlier code size assumptions, even if we managed to weed them down to 1/3 at each step, with one mutation per mutant, we would have 333 mutants per method, and a third, but I'm rounding. With two, we would already have almost 110,000. And then with three, we would have over 35 million. Never mind running the tests, just creating the mutants would get to be quite a heavy workload. But we can avoid the heavy workload and the lack of focus and the increased false alarms if we just limit it to one mutation per mutant. So to summarize at last, mutation testing is a powerful tool to ensure that our code is meaningful and our tests are strict. It's fairly easy to get started with in terms of setting up the tools and annotating the tests, which may be tedious, but at least it is easy. But it's not so easy to interpret the results, nor is it easy on the CPU. Even if these drawbacks mean it's not very well suited for our current project, I still think it's just a really cool idea in a geeky kind of way. If you'd like to try mutation testing for yourself, here's a list of some popular tools for some popular languages and frameworks, and some other ones. I doubt many of you are doing Fortran 77 these days. I'll talk a little longer so you can take pictures if you like. As for the ones about Ruby, Mutant is the main one, but they are moving to a closed source paid model, but they are leaving the last open source one out there for everyone to use for free. And I'm not entirely sure, but if I remember rightly, open source projects can use even the paid version for free. Mutest is a fork of an old version of Mutant, and work has continued on it, so it has some features Mutant doesn't, and vice versa. But it's only compatible with RSpec rather than Minitest. My current main client uses Minitest, so I didn't bother playing with Mutest much. Heckle hasn't been updated since 2013, so good luck with that. As for the rest of them, just be aware that, like for the other languages and so forth, just be aware that many of these may be outdated. I do not know or even just follow quite all of those languages. Everybody done taking pictures? Okay, moving on. Lastly, a shout out to TopTal, a consulting network I'm in that has a speakers network that helped me prepare and practice this presentation. Please use my referral link there if you want to hire us or join us. And many thanks to Marcus Sherp, who created Mutant, the main mutation testing tool I've actually used, and has been very willing to answer my questions and critique this presentation. And now it's your turn. We have about 5.5 minutes for questions. If you think of something later, there's my contact information up there, and of course I have cards and I'll be around for the rest of the conference. So any questions? Okay, how long does it take to get up and running with mutation testing on a project, to get your first, I guess it would be your first report of, here's some surviving mutants you should do something about. On a reasonable sized project, I suppose you could make a decent dent in it by just installing the tool and running it. How long that's going to take depends how big your code base is and whether your chosen tool skips methods that it doesn't find any tests for. a number of other factors. But I would guess with a not too huge Rails app or something like that, you could have an actionable set of mutant reports in under an hour. The most time-consuming part, at least in my experience, very limited, are waiting for the thing to actually run rather than the setup. And like I said, you can do that over a lunch break or overnight or something. And even more so than trying to figure out what the mutants are trying to tell you. That's why I consider this an advanced topic. A lot of it takes a lot of experience. Okay, when killing mutants, do I consider it more of a best practice to optimize a given test or add additional tests? And I would say that's really a subset of the philosophy of whether one does that overall in tests. What I generally do is write tests for specific situations I'm trying to make sure are covered. So for instance, with that initial example of the power method, I think I would have some functions to say, okay, what if some smartass passes in as 0? What if somebody passes in something otherwise invalid? And of course, a few cases for the normal usage, like 2 to the 3rd power or whatever. For that, I think I would try to just have 1 or 2, but not an excessive number, of fairly normal tests, chosen so as to not let a lot of mutants survive. It may be difficult with some kinds of functions to have 1 test kill a boatload of mutants, like nuke Magneto's headquarters or whatever. But like I said, no need to be a superhero about it. You can have 1 test kill that batch of mutants, another test kill that batch of mutants, which as you may notice is overlapping a little. Don't overthink it too much, I guess, would be the main thing. Okay, the question is, do Mutant and Mutest patch the Ruby interpreter to make this work? I don't think they do anything to the copy that you're actually using for most of your regular Ruby usage. I haven't taken a look at how they work under the hood, so they may make a copy and tweak that. I've done a little bit of other custom parsing stuff, and what I've seen done in that domain is mainly, okay, here's the grammar we're trying to use, have it go according to that, and may reveal a few additional things or ignore some things that the normal configuration would ignore. I don't think it does anything that would, I don't think either of those rather, would do anything that leaks into your other usage of the interpreter. We have 45 seconds. Anybody got a real quick question? All right, I guess then we get a little lead on everybody for the afternoon snacks. Thank you.